Hello, thanks for coming to view my presentation today. I'm Jeff Lowe, a Lillian Gilbreth postdoctoral fellow in the departments of chemical engineering and chemistry at Purdue University. And today I'm going to talk about work with my advisors Jeff Greeley and Christina Lee on looking at the feasibility of indium hydroxyoxide structures on platinum nanoparticles for the CO electrooxidation reaction. And this is ongoing work here at Purdue. Okay. Now, before we get started, I just want to mention, and should be able to go forward, that I'm a faculty candidate. And this presentation is one of 4 presentations that I have at AICHE this year. There's one other oral presentation on my work that I've been performing in my current postdoc at Purdue, one oral presentation for my PhD work at the University of Michigan, and a faculty candidate poster. I encourage you to check those out to find out more about me and my research. If you'd like to reach me to chat more about my research or my qualifications for a faculty opening at your institution, just send me an email. My email address is at the bottom of the slide and at the end of my talk as well. So in this work, we're looking at CO oxidation reaction in alkaline media. So why would we be interested in this reaction? Well, 2 reasons. First, this reaction is useful in hydrogen fuel cells to remove CO molecules that can hinder the hydrogen oxidation reaction or the HOR at the anode. Second, it's a simple probe reaction to analyze bifunctional reaction mechanisms since it only involves a single electron transfer as demonstrated by the overall reaction. What I mean by this being a bifunctional reaction is what's demonstrated in this image from the Markovich group at Argonne. In a system where there is submonolayer deposition of a metal hydroxyoxide film on a platinum surface, CO will adsorb at the platinum sites. OH is generated at the hydroxyoxide film, likely by enabling water dissociation. The CO and OH can combine to generate carbonate and subsequently form CO2. A few years back, the Markovich group showed that this bifunctional catalyst is able to outperform a pure platinum catalyst for a number of transition metal hydroxyoxide structures. Now, comparing the overpotentials for CO electrooxidation of first-row transition metals, with the exception of manganese shown here at the bottom right-hand corner of this plot, all of the catalysts outperformed a platinum 111 substrate. So platinum 111 being here, the other catalyst at lower overpotentials. In work by our group, we looked at the hydrogen evolution reaction, or the HER, using DFT in these types of systems. Much like CO oxidation, the HER activity may be improved with a bifunctional mechanism since water dissociation can occur at the metal hydroxyoxide cluster and hydrogen adsorption at the platinum surface. And we found that this catalyst indeed achieved reduced barriers for water dissociation as compared with the platinum 111 surface. Our barriers a bit below that, thus resulting in improved activities for the HER. However, in all of these systems, a reducible 3D transition metal is employed since conventional wisdom tells us that the metal should be able to pull electrons from the water to adsorb the neutral OH intermediate on the surface. But the question is this possible for other metals? So in a recent study by our group, we performed experiments on an expanded set of metals, including not only 3D transition metals, but also post-transition metals such as indium and gallium. In most cases, submonolayer metal oxide films were deposited on platinum nanoparticles, and the catalysts were evaluated for their CO electrooxidation activities. As expected, nickel, shown by this green curve here, outperformed platinum, as shown by the gray curve, displaying a lower overpotential for CO oxidation. But surprisingly, the highest performing catalysts actually involved indium, which achieved an overpotential 200 millivolts lower than that of platinum. So our question then became, how is this possible for a post-transition metal like indium, for which reduction is thermodynamically unfavorable? Let me remind you that indium is a group 13 metal, so it prefers to give up 3 electrons and is normally in the 3+ oxidation state. Well, our hypotheses for why this is occurring are 1, the stability of indium hydroxyoxide phases is modified by the presence of the platinum surface. So in other words, the stability trends of these phases are modified when they are present as a thin film on a platinum surface as compared to their stabilities in the bulk. And 2, under-coordinated indium sites, which are present on the lowest energy indium oxide surface, have been shown to facilitate the cleavage of water molecules in the literature. So this nice paper from the Diebold group in Austria demonstrated both experimentally and computationally that water dissociation is favorable on indium oxide surfaces at low temperatures, around 100 Kelvin. Starting with the first hypothesis, we tested this by looking at bulk versus surface stability trends for various indium hydroxyoxide phases using DFT. And let's start with the bulk trends. On the right, I'm showing a plot of the free energy of formation of various indium hydroxyoxide phases under alkaline conditions, in this case at pH 13. The energies of these phases are computed relative to the indate ion, or the ion O2 negative ion, which is the stable substance at this pH from the Pourbaix diagram. The x-axis is the potential relative to the reversible hydrogen electrode. The way to interpret this diagram is to look at the phases with the lowest energy as a function of potential. So, starting with the low potential region, indium metal is the stable phase. Then, going to intermediate potentials, indium hydroxide, or ion OH3, becomes the stable phase. Of note here, there are three phases, all of which where indium is in the 3+ oxidation state, and all within about 0.3 electron volts of each other. So it's possible that these three phases may actually coexist in this range. The other two phases are indium oxide, ion 2O3, and indium oxyhydroxide, ion OOH. And as a reminder, the potential range most relevant for CO oxidation is in the roughly 0.3 to 0.7 volt region, which falls in the middle of this intermediate region. And finally, at high potentials, ion O3 becomes the stable phase. Now we're going to look at the surface stabilities, but before I do that, I want to mention that we've done some experimental characterization to better understand the structure of the experimental system that I mentioned a few slides back. And from X-ray photoelectron spectroscopy, or XPS, it appears that the oxidation state of indium is 3+, which may initially indicate that we have one of three phases that appear as horizontal lines present. Nonetheless, on the surface, it may be possible for indium to exist in the 3+ oxidation state, but be present in a different phase. For instance, the ion O2 phase could be present since the platinum surface can actually pull electron density from the oxygen atoms in ion O2 and allow indium to stay 3+. So let's look at surface stabilities. And to show you how we've done this, I'm going to use the ion 2O3 phase as an example. Now, creating the surface structures is non-trivial since the indium oxide phase can adopt a number of possible structures. So to simplify our analysis, we assume that the oxide layer forms a monolayer on the platinum substrate. And we limit our analysis to the platinum 111 facet since it will be the most prevalent facet on a platinum nanoparticle. To construct the indium oxide monolayer, we assume that it adopts an FCC unit cell to match that of platinum, and we generate an indium oxide unit cell where the indium-indium and indium oxide, or indium oxygen distances match those in bulk ion 2O3. We tested various placements of oxygen atoms and selected the placement that gave the lowest energy structure. Then we build a set of interfaces with varying indium to platinum ratios by expanding the platinum and indium oxide structures into supercells, where the lattice parameter of the indium oxide layer was strained to match that of the platinum layer. And finally, we computed the formation energy to determine the lowest energy interface using this equation here. And basically this gives the energy of the interface relative to platinum 111 surface and bulk ion 2O3, normalized by the number of formula units of ion 2O3. This analysis generates the plot shown to the left, which shows the formation energy relative to the interface indium to platinum ratio. And this ratio only includes platinum atoms in the top surface layer. And as you can see, there's a fairly complex relationship between formation energy and indium to platinum ratio. But we can break this formation energy down into two components. One, the film formation energy, which is the energy to create a monolayer film of indium oxide from bulk indium oxide. This term follows an equation of state type shape, where the lowest strain structure is at the minimum. The bond distances in the indium oxide film are elongated to the left of the minimum, where the indium to platinum ratio decreases, resulting in a tensile strain. And the indium oxide bonds are contracted to the right of the minimum where the indium to platinum ratio increases, resulting in a compressive strain. Note that the film formation energy is always positive, since it takes energy to create a surface film from the bulk. And 2 is the adhesion energy, which is the energy of stabilization in creating an interface between indium oxide and platinum based on a favorable interaction between the two films. This term is always negative since it's a favorable interaction. And as you can see, there's an overlap of the extrema in the two curves around an indium to platinum ratio of 0.6. This gives the optimum structure from the standpoint of the formation energy, which is a summation of both terms. The structure with the lowest formation energy occurs at a ratio of 0.64. So now we can take a look at the structure. We can note that it includes indium atoms with differing oxygen coordination environments, or different coordination environments of oxygen atoms around the indium atoms. And if you remember from earlier in the presentation, I said that this was a key feature of the lowest energy ion 203 termination, the 111 surface. So if we cleave the indium oxide 111 surface and put it on a platinum 111 substrate, the structure with the lowest strain, which happens to be the 111 supercell of ion 203 and a 5x5 supercell platinum, gives us this. Very interestingly, it's the exact same indium to platinum ratio and a nearly identical structure to what we obtained using the procedure I outlined. And if I additionally then compare it to the ion 203-111 structure from the literature, there's also a close match. So I guess we really could have saved ourselves some time. But however, we do learn a lot more about the energetic profile using this approach. And we can see which structures are similar in energy to this lowest energy structure. This is important because this interface is quite large, 115 atoms, which can be challenging to model with DFT. In particular, this is challenging when looking at reaction kinetics. Now, given the favorability of water dissociation on ion 203-111, as shown in the literature, we are also investigating various hydroxide surface compositions, which might be more prevalent than the indium oxide phases under electrochemical conditions. And I'm currently using the procedure just outlined to look at the surface stabilities of each of the bulk compounds that I showed earlier in this presentation. This work is ongoing, but it's important to get the structural details correct in order to give the best agreement between computation and experiment. So to summarize, in our experimental efforts, we found that indium hydroxyoxide species on platinum nanoparticles were surprisingly effective catalysts for the CO electrooxidation reaction in alkaline environments. In the current presentation, I showed you our ongoing efforts in calculating bulk versus surface stability trends for these indium hydroxyoxide phases on platinum surfaces using DFT. And I showed that for the ion 203 film, the lowest energy interface is at an indium to platinum ratio of 0.64, with the structure of the with the structure that's consistent with that of the ion 203-111 surface. Going forward, our plans are to complete the surface stability analysis and to use the results to understand kinetic behavior in these systems. In particular, we're interested in computing water dissociation barriers at triple phase boundaries, where water is present explicitly, and in computing the barriers for adsorbed CO and OH combination, which could potentially be the rate determining step in some environments. Now, more experimental characterization of the indium hydroxyoxide structure on the platinum nanoparticles is also planned in the future work. I'd like to thank members of both my groups, in particular Dr. Zhenhua Zhang for his valuable discussions that have really steered my work, and my advisors, Jeff Greeley and Christina Lee, for their support and guidance in these efforts. I would also like to thank the College of Engineering at Purdue for funding my fellowship so that I can explore these interesting challenges, and the Davidson School of Chemical Engineering for conference support. As a reminder, I've scheduled a simultaneous Q&A and live session if you want to ask me questions on this work. If so, I look forward to seeing you there. If you're not able to attend, just send me an email down here at the bottom of the slide. And thank you very much for viewing my presentation today.